Okay, good morning. Everything looks right. Okay, welcome. Right, some of you in Zoom, some of you in on YouTube, however you like to do it. So today we are getting into this new stuff, radicals. So radicals are basically roots, square roots, cube roots, stuff like that. And it's kind of like exponents, where it starts off real basic, but then it gets kind of complicated at some point. Okay, so this is another one of those chapters where there's tons of little details, right? There's like, you'll do all these different problems, and you can't memorize how to do it, right? I know I've railed against that in just math classes in general, and I know a lot of students stick to trying to memorize everything, kind of because that's what they know, that's what they're comfortable with. But the further you go in your college classes, it's just not going to work. You're not going to be able to memorize everything that you can. So this is another one of those chapters where you want to bring your toolbox. You're not going to be able to memorize how to do everything. You want to bring a toolbox where you're like, well, I have all these different tools for dealing with roots, and here's one of them, right? And you pull it out and you try to use it, and maybe it works, maybe it doesn't. You try to do something else, and eventually you're going to get comfortable with that toolbox, and you're going to know when to use the different pieces that you need to use, when to use the different parts of the toolbox. So we're going to start off basic stuff that's not too bad, and then it'll get more and more complicated as we go through things. Whoops, and I didn't even open my book to the right page here. Let me do that. Make sure I don't forget. There's a ton of details. We want to make sure we don't forget how this works. So we have a thing called perfect squares. Okay, so perfect squares. Let's see, actually. Sorry, I'm just looking at due dates. It's clear I'm going to have to extend this topic a little bit. So a couple of these assignments, I'm going to write it down right now. I'm going to have to give you more days, right? We're starting to talk about on the 8th, and on these 3 chapters are due on the 11th. That's not quite enough. So I'm going to take these 3 assignments right here, and I'm going to make you have a little bit more time on them. In fact, why don't I do that now? So radical simplification, radical equations, complex numbers. That's just too soon. Oh, I don't think I can do that without showing people's grades. So let me just make a note. MV03 complex numbers. Didn't realize till just now that they were due in a couple days. Radical simplification and radical equations. Yeah, you're going to want a little more time with those. So I'll give you some more time. So, right, so I will, at some point today, I will extend those homework assignments so that you have ample time to work on them. And the next assignments aren't due till like, well, there's a couple little ones here, but I'll have to look at. See, then we have other stuff that's not due till the 25th. So we have a little bit of time to spread things out a little bit. Remember, those of you used to have a little bit more time on the retake. Actually, you have a bunch more time on the retake. So if you're trying to get that done, make sure you don't miss the window, because it won't get extended past that period. Okay, let's get into what we're talking about. What are we talking about here? Well, we're going to have things that involve roots. So square roots are most common. Most common calculators have a square root button. Some calculators have an nth root button where you can take cube roots and fourth roots and fifth roots and all sorts of fancy things. But in both in mathematics classes and in the real world, by far the thing you're going to deal with the most is the square root, which is the simplest one to deal with. If you want to deal with the other ones, you just sort of extend the ideas. But the square root's probably 95% of the time, that's what you're going to be dealing with. So let's take a look. So what does this mean, right? Well, we can think about the math a couple ways. And I have stuff left over from the earlier class. Let's clean that up. So let's just take, for example, the fact that 4 times 4 equals 16, right? So it's kind of that reverse order we were doing before with factoring and multiplication. You've got factoring, the reverse operation is multiplication. Here we have multiplying, but this is with a special type of numbers, specific numbers. Why are we not compiling that? Oh, here we go. 4 times 4 is 16. So if 4 times 4 is 16, then we have this special language that says that 16 is what we call a perfect square. Now think about it this way. If you were making some geometric shape, a garden, a patio, whatever, and it was going to be 4 feet by 4 feet, what shape would that be? It would be a square. Right? So that's why we call it a square, because if you have a rectangle and the two sides are equal to each other, right, the adjacent sides are equal to each other, then you have a square. Okay? So we call 16 a perfect square because it's some number times itself. There's a bunch of these, right? 4 is a perfect square because it's 2 times 2. 9 is a perfect square, it's 3 times 3. 5 is a perfect 25 is a perfect square because it's 5 times 5. 36 is a perfect square because it's 6 times 6. So you get the pattern here, right? 100 is a perfect square because it's 10 times 10. 144 is a perfect square because it's 12 times 12, right? Many of you know those already because most places you still have to learn your multiplication table. Some places they've stopped teaching it, but by and large, you still need to do those. You'll learn, you want to get comfortable with those squares. It's going to be helpful in this chapter. So just, when a 49 comes up, you go, oh, yeah, that's a perfect square. When 81 pops up, you go, oh, yeah, that's 9 times 9. You just want to get comfortable with those perfect squares. They're going to keep coming up in the problems, so you'll be seeing them more and more. So it just you'll just naturally get used to them. You will have some problems where you have to know the cubes, but the good news is since those get so big so fast, we usually don't give you as big of cubes. So like 8, you want to recognize that 8 is a perfect cube. It's 2 times 2 times 2. So a cube is the same idea as the square, except it's 3-dimensional, right? If we say, if you had a cube whose volume was 8, what would the sides be? 2. 2 times 2 times 2, right? 27 is a cube. It's 3 times 3 times 3. 64 is a cube. It's 4 times 4 times 4. You see how these numbers are getting pretty big, pretty fast? So you're not going to see as many of those, but you will see 8 come up a lot, 125, 64, those smaller cubes, you will start to see in the homeworks, and some of you will start to recognize them and memorize those. Okay, so we have this other language then that says, well, what if I want to know what the number is? Like, let's say I know that a number is a perfect square, but I want to know what that number is. So let's say I have a square. I make a patio in my backyard, and I know that the area of that patio is 16 square meters. How could I figure out the length of a side? Okay, and the answer is you would take the square root. But what I'm trying to show is we're turning the question around on itself. We're taking an area and trying to figure out, well, what's the size that would give me this proper area? So the way we would write this then, another way of conveying the same information is that the square root of 16 equals 4. Okay, the square root of 16 equals 4. Now, we actually call this thing the principal square root. And you may not have heard that before because no one ever actually says it. But it's understood when you see the square root symbol that we mean the principal square root. Now, what does that mean? Well, there's actually 2 ways this could work, right? Look at our first equation. 4 times 4 equals 16. Is there another number that when you multiply it by itself, you get 16? Yeah, there is. It's -4 times -4. So then, couldn't you make the argument that, well, the square root of 16 is also -4? And the answer is no. When we say the principal square root, we are specifically saying don't consider the negative ones. In other words, we're getting rid of this possibility right here. And the reason we do that is most of the time we care about square roots, we don't want to get into negative numbers. It gets really complicated really fast. Because most of the time, if we're doing something geometric, we probably don't care about the negative part. If we're doing something in basic calculations, we're usually wanting the positive. So it's nice. You can actually just assume, yeah, we mean the positive one. Whenever you see a square root, that means we want the positive answer. You ignore the negative one. Okay. We will get into something a little later called complex numbers, where we deal with square roots of negatives, but that's a very special situation. Square roots of negatives and that kind of stuff in general leads to this whole course called complex analysis. Those of you who are going into engineering, or depending on which type of engineering, or if you're a math major, you'll have to take that course down the road. We don't have to get into that. We're just going to go only as far as complex numbers and leave it at that. Most people don't need to go beyond that. Okay, so just always realize we mean the positive one. Okay? However, we can play around with this a little bit. What if I had this, but I said, what if I put a negative in front of the square root? Well, that's okay. That's still allowable, right? Because I'm not trying to take the square root of a negative number. Like, what's wrong with taking the square root of a negative number? Well, when you multiply a number by itself, it becomes positive, right? If you multiply a positive number by itself, you get a positive. If you multiply a negative number by itself, you get a positive. So how could we get a square root of a negative? You can't. It's not in the real numbers. Then we have to introduce the complex numbers, which we'll do in a couple weeks. But this is allowable, where I can have a negative out front, because you still know how to simplify the square root of 16. You get 4, and then this negative in front carries over, and that tells us that our final answer should be -4. So there's just tons of little details in this chapter that you got to look out for. Square root on the outside, that's fine. Square root on the inside, that's problematic for now. So that's what I mean. It's just too many tiny details to try to memorize everything. You're going to be much better off just trying to remember how it is that this stuff works. Okay? So for now, what we'll do, I forget what it says on Delta Math, but usually if we try to take the square root of, say, -16, like this, then what we would say for now is not a real number. Not a real number. So in other words, it's not in the real numbers. This language confuses people, and I wish we would change the naming convention for these, because it really it's misleading to people. It gives the wrong impression. When we say not a real number, people go, oh, so it's just some like made up math thing. No, we mean it's not in the real number system. If you wanted to take the square root of -16, you can do it, but you have to employ the complex numbers, which we'll learn about in a week or two. Complex numbers are totally valid, but the fact that they're sometimes called imaginary numbers, the fact that this number system we deal with is called the real numbers, that's just left over from history, because the Greeks couldn't figure out what to do with these things. And they're like, okay, you get these mathematical numbers, but those are just sort of math exercises. They don't really relate to anything in the real world. So they called what we're used to using the real numbers, and these other complex numbers, they called them imaginary numbers. And the name just kind of stuck. But it's unfortunate, because it leads people to think that the complex numbers and the imaginary numbers don't count because they're not, quote unquote, real numbers. But the reality is, we would not live in the society we live in without complex numbers. You wouldn't have any kind of computing. Any electrical engineers have to use complex numbers to represent voltages. So any kind of thing that requires electronics, anything like that, you're using complex numbers. So just when I'm throwing around this language, just be aware early on when you're hearing a lot of it that it's not to say this is the important set of numbers, and this other thing over here is just some made up thing that your math teachers like you to do. It's all applicable to the real world. We've just named it really poorly. So later on, we're going to learn what to do with square root of -16. For now, we don't know what to do with it. It doesn't make much sense to us. Say we want to get into the square root of x squared. Okay, so I'm asking myself, what do I multiply by itself to get x squared? And the answer is x, right? The answer is x. So it doesn't change a lot with variables. The between numbers and variables, you're just asking, what do I multiply by itself to get this particular thing, okay? Right. Oh, fractions. Square roots of fractions seemed like they'd be hard. They're not. They're actually quite nice. So let's take, for example, the fraction. We want to take the square, oops, let me do this right. I want the square root of the fraction 49 fourths. Now, a lot of times in mathematics, the thing that people want to do, you look in the equation, you'd be like, man, it sure would be easy if I could do this thing. Usually that's not the right thing to do, right? The easiest way is usually mathematically incorrect. But what you want to do in this case actually ends up being the thing that is the right thing to do. We will have some choices here. You're going to have choices in this chapter about how to do certain problems. This is one. Fractions, we have a choice. I could either, if I know the square root of the whole fraction, I can just take it directly. Or what we can do is we can think about it and break it up into the square root of the numerator and the square root of the denominator. So this is a common thing that we do in mathematics, where we take a complicated problem and we break it down into two simpler problems. So this becomes the square root of 49 over the square root of 4 and those are pretty easy to do. The square root of 49 is 7. Square root of 4 is 2. And there you have your answer, right? So actually, fractions, when you're dealing with square roots, pretty easy to do, right? So the square root of 49 fourths is 7 halves. It's really convenient the way that it works out with fractions. Decimals, play around with your decimals. It makes sense, but some people just get a little confused about which way they're moving the decimal. Just think about it in terms of the multiplication, right? If I multiplied this number by itself, would I get the thing I'm looking for? And then, work on that. So you can practice that. Get the graph. We don't care about that. Let's jump over and take a look at a problem or two. Okay, so let's see. I've got x cubed times the square root of x to the 6th. Okay, so we've got some things to deal with here. Let's think about this. What would let's copy it back over. X cubed square root of x to the 6th. Let's go to a new page. X cubed times the square root of x to the 6th. Okay, so there's our problem from the previous page, right? Yeah. Okay, well, there's not much I can do with x cubed, but what I can do is simplify the square root of x to the 6th. So I ask myself, okay, thinking back to my rules of exponents, what would I multiply by itself to get x to the 6th? Right, well, let's see. It would be when I multiply x cubed times x cubed, because that's when you add the exponents. So x cubed times x cubed is x to the 6th. So this would become x cubed times x cubed. The square root of x to the 6th would simplify to x cubed. Now we know from our rules of exponents I'm supposed to add these together. See how those rules of exponents are going to keep coming up? You'd be surprised how often they're going to come up in this chapter. Then we add those together. We get x to the 6th. So our final answer for this problem should be x to the 6th. So I go back. Luckily, that's one of my options. Good. Submit my answer. Yeah, I'm pretty sure that's right. There we go. And we're good. So see how they did the same thing I did. So you're just going to go through and do those problems. Simplify these. In fact, this one's like the same. I'm going to get this one wrong on purpose. Let's see what the next one looks like. Okay, 7x to the 5th. What do we do with something like that? So the square root of 7x to the 5th. Let's do that one. All right, so I've got the square root of 7x to the 5th. This one's not going to come out clean. So we're going to have to break this up into the part that simplifies nicely and the part that does not. So basically, like the leftover you leave inside the square root, the part you can bring out, you do. So I'm going to break this up into 2 square roots here, and you can see the part that's going to simplify and the part that is not. So the 7 has to go in the leftover piece. Square root of 7, there is a square root of 7. In fact, I'll show you, but we don't use it because, well, we don't use it in the decimal form because the decimal form is actually an approximation. See, if I take this and I go 7 square root, I get 2.64575131106, like all these digits. That's because it's an irrational number, like pi and e, where they have an infinite non-repeating decimal expansion. That's not very convenient for writing a decimal number. So instead of writing the square root of 7 as this weird decimal and then approximating it, we just write it as square root of 7. We like leave it in there, okay? Now the x to the 5th, I want to break that down into part that I can simplify and part that I can't. Well, I think that I should be able to should be able to reduce the x to the 4th, but then I'm going to have one x left over because there's 5 x's in x to the 5th. I think I can reduce 4. That leaves us 1 left over. So this here is how we break that down. This first piece, what is the square root of x to the 4th? Well, what do I multiply by itself to get x to the 4th? The answer is x squared. And then what I'm left with is the leftover piece, the 7x, the square root of 7x piece. So this should be our final answer, x squared 7 square root of 7x. So what you're always doing is you're looking for something inside the square root that you can break apart multiplicatively and then pull out a perfect square. So x squared, or x to the 4th is a perfect square. We can simplify that. If there was a number in here like 16, we'd try to pull that into the part we can reduce, and then you have your leftovers here. So let's take a look. This would be, yep, here's the one we got, I think. Let's say we got it. So see how they split it up, the perfect square part and the leftover. So that's how you go there. Yeah. So this will be 3 root x because the 9 we can pull out and simplify in the root. The x gets left over. See about the next one. Yeah. Okay. So I think we're good on that one. Okay, so what they're going to do, I was a little, I sort of skipped a couple details when I talked about when I talked about the square root, technically when you take the square root of x squared, it's the absolute value of x, but then what all these computers do is they just say, assume x is greater than 0 anyway, so you don't have to worry about that negative part. It's a little different when we have cubes because you like, let me show you. Let's look at the cube. The cube kind of operates a little bit differently than the square. So if I take, let me show you. Then we'll go back to that problem. So what does this mean? This means the cube root of 27. So this little number here, this 3 floating in there, notice how it's inside of the corner right here. It's not out in front. See, like here the x squared is out in front of the square root symbol. That means you multiply. Here, this 3 is part of the square root symbol. It's called the index. It's telling us that we're dealing with a cube root rather than a square root. So remember when I took the square root of x squared, I was asking myself, what do I multiply by itself to get x to the 4th? Here I'm asking, what do I multiply by itself and then multiply by itself again to get 27? So what number do I multiply 3 times to get 27? And the answer is 3. Okay. Oh, okay. Okay. But notice there's a difference here. Remember how I just talked before about how you can't take the square root of negative 16 till we have complex numbers? You can take the cube root of negative 27, right? So let's take a look at this. This actually ends up being -3. So you can take the cube root of a negative. If your index is odd, negatives are okay. If the index is even, like if you try to take the fourth root of a negative, if you try to take the square root of the negative, you need complex numbers. So why is this? Well, -3 times -3 is +9, times -3 again gives you -27. So you can take the cube root of a negative. You get -3. Okay, so with that said, back to here. Here they're specifically saying, given that x is greater than 0, they're trying to get you to stay away from negative numbers in certain problems. So the cube root of x to the 27th, that's a little different. We just looked at the cube root of 27. Now we're looking at the cube root of x to the 27th. So this is where people start to get confused between exponents, and it's because they're forgetting the exponent rules, right? What would the situation be that I multiply things by themselves to get x to the 27th? Remember, in that case, we add exponents. So x to the 9th times x to the 9th is x to the 18th, times x to the 9th would be x to the 27th. So our answer here should be x to the 9th. And they like that. Yeah, they like my answer. I don't really love their explanation because it doesn't really explain why, but it's true. What they're writing here is true, but I feel like it's not a good way to represent the problem. Okay, so you're going to play around with those a little bit. Let's see. This should be what? X to the 10th. Yeah, and they're just telling you here's how you do it. What's the next one? Okay, this one's a little bit more complicated. Let's take a look at it. Square root of 16. So, remember I was just telling you about the index? This 3 here means cube root. When there's no number written there, it's understood to be a 2. In other words, a square root. So the square root, we don't usually write the index. Just like when we write 1x, we don't put the 1 in there. We just know x means 1x, right? So it's the same thing here. So we only write the number of the index if it's not a 2. So we wanted what? Square root of 16x to the 14th? Okay, let's look at that. So the square root of 16x to the 14th. Okay, so remember what I'm going to try to do is break this off into the pieces that I think I can simplify perfectly in the square root versus the leftover pieces. Well, 16, we already know. We've looked at that today. That should be a perfect square. So 16 is going to go in this first part. Now, what about the x to the 14th? I need to know how am I going to break that down into the piece I can reduce and the piece I can't. Well, I suspect that I can reduce, let's see, this is a square root. Oh, I was still thinking about cube roots from the last problem. This will just be x to the 14th. So I was thinking this was a cube root problem, but it'll still work out. X to the 14th, which means we're going to have the square root of 16 is 4, and the square root of x to the 14th is x to the 7th. So our answer should be 4x to the 7th when we've got it fully simplified. So let's see. 4x to the 7th, if I didn't miss anything we're doing. Nope, looks like that's all good. Okay. So let's go back and take a look. Okay, type 2. Actually, these are all just okay, let's see. For this one, all you're really going to do is there's actually a couple ways you can approach this. We have a rule that says, let's go to a new page. Now, there's a little bit of a caveat here, but this is a square root rule that is very convenient for us. It says that the square root of a times the square root of b is equal to the square root of ab. That means that if we have things inside a square root that are being multiplied, we can separate them into separate square roots. This is important because we can't do the same thing with addition. People try, it doesn't work. So that means that sometimes it may be in your benefit to combine the square root together and simplify it that way, or it may be in our best interest to split these apart and treat them separately. We've already been doing that. So you'll do both of these, where you split them apart or you put them together. Okay. Now, technically, this only works if both of your square root of A and square root of B represent real numbers. You'll see this rule fails when we bring up complex numbers in a week or so. So just be aware, even though I didn't write it out here, this only works when you're dealing with real numbers. Okay. So why I mention that is here, what we could do, depending on how we do this, is we could just, actually, I didn't recognize this was a cube root problem. We can't do this one yet. Actually, I thought this was 2 square roots. If this was 2 square roots, what you could do is you could combine it into one big square root problem if you wanted. Or you could separate it into a bunch of smaller problems and then combine from there. The fact that it's a square root times a cube root means that I can't do that until we can write things as fractional exponents, which we can't do quite yet. So we'll get back to that in a few minutes. Yeah, let's do that. So let's go ahead and get to fractional exponents. That sounds scary, right? Exponents, and then you're putting fractions in your exponents. It's not as bad as it seems. In fact, it's extremely convenient. So here's how we define things. A raised to the fraction m over n can be interpreted 2 ways, and you get to choose which way to interpret it depending on which way is going to make the problem simpler, right? So that's what I mean. There's like some really convenient stuff in this chapter. The unfortunate thing is there's so many things you have to remember. So how do I interpret A being raised to a fractional power? What does that mean? Like we can understand x cubed. That makes sense. X times x times x, right? You're multiplying x 3 times. How do I raise A? I raise it to the power of a fraction. I multiply it by itself a fractional number of times. What does that even mean? And here's where, we have to really think about it in order to make sense of what that means. The interpretation is, here's one of the interpretations. It becomes the nth square root of a to the m. But there's a second interpretation we can use. Like I say, you pick it. You decide which one you want to do. It becomes this. So these are your 2 ways of interpreting a fractional exponent. Okay, so either you can take the power first and then take the root. The numerator is the power. The root is the denominator. So you can either take the power first and then take the root of it, or you can take the root and then take the power. Usually, I would say 80% of the time, the second way is the one that's easier. Occasionally, you have to use the first way. It just depends. The problem with this way up here is if you take the power first, your number can get so big that you don't recognize it anymore. Whereas if you take the nth root, the number gets smaller and usually easier to deal with. So interpretation number 2 will work for you most of the time. That's super weird that it messed up. It compiled this first variable wrong. It's using the wrong font. That's super weird that it did that. Huh. Strange. Okay. Anyways, it doesn't matter. So that seems confusing, right? That's okay. Watch. I'll show you it's not bad at all. Let's look at an actual example. Let's take 8 raised to the 2/3 power. 8 to the 2/3. How am I supposed to multiply 8 to the 2/3? Well, I'm going to use this second interpretation down here. So that means that I am taking the cube root of 8, and then I'm going to square that thing. Right? So see how my numerator is the one that becomes the power on the outside, and the denominator is the one that becomes my root. Okay? Well, what's the cube root of 8? Well, I talked about this earlier. 2 times 2 times 2 is 8. The cube root of 8 is 2. So that means that this simplifies to 2 squared, which of course is easy now. The answer is 4. Okay, so you take a problem like 8 to the 2/3, which sounds super confusing and weird, but as soon as you use this formula to convert it, you go, oh, that's not bad. The cube root of 8 is 2, so now I have 2 squared. Now that's just 4. Okay. So maybe we'll go back and do this one. So that means we can also take something that's in radical form and we can convert it to having a fractional exponent. Okay, so let's do another one just to make sure you're comfortable with these. Okay, so I've got 32x to the 10th. I want to raise that to the 1/5. So I start thinking about, okay, what's the, I'm going to interpret this as the square root. It's going to be the 5th root of 32x to the 10th. Now, when you're not sure about some of these powers, like you're like, I don't really know any 5th powers. Well, you just play with them a little bit, right? Pick a number, because like I say, the higher that power is, the less likely that we're, I'm not going to give you like 19 to the 5th, because who knows all those numbers? I don't know what 19 to the 5th is off the top of my head. Start playing around. So pick one. Well, let's see. I'm looking for something whose 5th power is 32. So it must be pretty small. Just start with 2. 2, 4, 8, 16, 32. Oh, that does it. 2 to the 5th is 32. So this becomes 2. And then x to the 10th. Well, what would I multiply 5 times to get x to the 10th? Oh, that would just be x squared. So 2x squared would actually be the 32x to the 10th to the 1/5. Okay, that's what that thing is. All right, let's do this hard one here. This is a little, it's not that hard, but there's a little more going on. So square root of 49x to the 10th. So the square root of 49x to the 10th. And I'm going to multiply that by the square root. Actually, the cube root, right? The cube root of 8x to the 11th. So we've got 8x to the 11th. Now, I almost kind of hate showing a problem like this because, oops, gotta remove that and put it back over here. The thing is, I can think of like, I don't know, at least 4 different ways to do this problem that's going to make it work by applying the rules in a different order. But then sometimes students watch and they go, oh, I was going to use this one move. I wonder why I'm wrong. You're not necessarily wrong. It's just that there are numerous ways to do this problem. So your way that you're thinking about this may be perfectly valid. Everyone's brain works a little bit differently. and acts a little bit differently. So if your brain thinks about this problem in a different way that is legitimate, that's fine. Don't think you have to do the exact same steps that I did. So we have a square root and a cube root. How are we going to put those things together, right? Up here, when we had this rule, well, notice these are the same index. These are both square roots being multiplied. So I can't mix a square root and a cube root directly. What am I supposed to do? And the answer is you bring in those fractional exponents. Now, how you bring them in is up to you. I'm going to try to do a little simplifying first to make my life easier, and then I'm going to deal with the rational exponents. But if you wanted to bring in the fractional exponents right from step one, there's nothing wrong with that. That's totally fine to do. You're okay doing that. Okay, so let's take a look. What am I going to do? Well, I look at that first square root, and I think that actually has a perfect square root. The square root of 49 is 7, and the square root of x to the 10th will be x to the 5th, right? Okay, so that whole first square root simplifies. Okay, what am I going to do with the, and actually in this case, I thought they were going to want us to do, I thought this problem was going to come out differently because there's, later in the chapter, there's similar problems where you have to do something a little bit more clever. So I thought this problem was going to go a little differently. Okay, so the first part is 7x to the 5th. What about that cube root of 8? Oh, well, I know what the cube root of 8 is, right? Because it keeps coming up in these problems. Cube root of 8 is 2. But then what about my cube root of x to the 11th? Well, what would I multiply by itself 3 times that could get me near that? Well, x cubed times x cubed times x cubed would give me x to the 9th. So this is x cubed. But I'm going to be left with still a cube root with 2 of those leftover x's, so x squared. Do you see how those don't get simplified? If you have a question, let me know, because I know this can be confusing when you're seeing it for the first time. So if you're not sure, let me know. So we should be able to simplify all of that. So I'm going to get 14x to the 8th times the cube root, the cube root of x squared. So let's see. It's I can mess these up too. So let's see if I got it right. 14x to the 8th. 14x to the 8th. Okay, so also, just so you know, a couple ways you can do this. There's a square root button down here, so you can press the square root button, although I should get out of the exponent first. So you do that by either going over or down using the arrow keys. That gets you out of the exponent. Now that I'm out of there, I can hit square root. Or the other thing you can do, if you don't, again, it's this thing, the more you use computers, you realize it actually takes a ton of time to reach for the mouse all the time. So people that actually spend a lot of time on computers, they like to use the shortcuts. So if you type, watch, so I'll do SQR. As soon as I type T, it recognizes that SQRT is it's usually used in computing to represent square root. So as soon as I hit T, it gives me that square root sign. So if you're someone who doesn't like to keep grabbing for the mouse all the time, just type SQRT. For some people, that's actually significantly faster. Otherwise, nothing wrong with hitting the button down here for the square root button. They're both totally legit. Okay. So what did I get? 14x to the 8th. The cube root. Oh, it should be the cube root. So it lets me put the 3 up there, and then I get the cube root of x squared. Now, you want to be careful. I definitely see people get confused between, see how this 3 is up here? That's the index. And then we have like this other stuff over here. This is not x to the 83rd. One is the index. One is an exponent. You want to make sure you recognize the difference between the stuff that's in front of the square root and the stuff that's part of the square root, like the 3 there. Okay. And I got it. And they did the same thing I did. Oh, and they used the fractional exponents, which you totally, I mean, there's so many choices about how to do a lot of these problems. So solving it with rational exponents, totally fine. Doing it the way I did it, totally fine. They're all legit ways of doing the problem. Okay. And with that, I think I'm not going to be able to get another problem in there. So we will continue with this next time. I'm going to extend those due dates here in the next few minutes, so you'll have more time to deal with that homework, getting those homework assignments done. And then you can bring questions, whatever you need. I do have office hours today, so feel free to hop over into Zoom if you want to talk to me about stuff. Otherwise, I'll see you in a couple days. Keep up the good work. Remember, there's a retake option available to you. So if you wanted to retake that test, just remember, if you retake the test, it replaces your original score. That could be good, but if you don't prepare, it could backfire on you. However, like I said, the people who study for the test basically never get lower. So do what you need to do. Otherwise, if you got a grade you can live with, by all means, live with it and don't do the retake, okay? Whatever works for you, whatever you think is the best decision for you as a student. Okay, thanks, everybody. We'll